Hello everyone, welcome to all of you to my YouTube channel. Here in this session, I'm going to discuss the segregation model, which is from non-ideal reactor. So let's try to understand the concept. Okay, so it's very important topic. I mean, whenever you see the problem on the gate exam, and even if in the work, there is a high probability to ask the question on from this concept. Okay, so let's try to understand the concept first. So my dear student, when we talk about segregation model. First of all, we need to understand, when we are going to design the reactor, okay, so there are two aspects, that is ideality and non-ideality. So here I am discussing about the non-ideality part of the reactor. So, the mixing pattern of the fluid inside the reactor, is one of the most important factor for the controlling the behavior of the reactors. Okay, so when we talk about the, how the fluid will be behaving inside the reactor and how we can design the non-ideal reactor. So, the mixing of the fluid becomes very important. And fortunately, my dear student, will see the first order reaction is the only reaction whose conversion is only depends upon the residence time. Okay, we are having only first order reaction whose conversion is only depends upon the residence time. Okay, and it's independent of the initial concentration. Okay, of the reactant species. Okay, so what happens in the mixing of the surrounding fluids, the element is not important for the first order reaction, but it is not the same for the second order reaction or any another order reaction. So means in case of first order reactions, what happens, the conversion only depends upon the residence time. It does not get deviated, or it does not depends upon the the elements of the surroundings. Okay, so but what happens here when we talk about the second order reaction and the third order reaction, so what will happen, or zero order reaction, so what happens in that particular case? Okay, so hence only RTD is not sufficient to determine the conversion of the performance of the reactor. Okay, so when we talk about when so here I can write only first order reaction. In only first order reaction, conversion is the only function of residence time. Are you getting? In only first order reaction, conversion is only the function of residence time, my dear student. Okay, but when we talk about, my dear student, other order reaction, just like uh, zeroth order, second order, generally we study this particular thing, third order reaction. Okay, third order reaction. So here what happens, RTD only is not sufficient to determine the conversion of the reactor. Okay, so you can write RTD only not sufficient to determine the conversion from the. So it is happening in which case? It is happening for the order having zero order reaction, second order reaction, and third order reaction. Okay. But in case of first order reaction, already I have told you, it is only depends upon the residence time or RTD function. Okay. But for this particular reaction, RTD is not sufficient for determine the conversion of the reactant. So what will come to play in this role? So my dear student, here for the conversion, one factor will be RTD, plus second thing will be kinetics of the reaction, that is first order second year, and third will be, my dear student, modeling parameter. Modeling parameter. Okay, all these three becomes very important when we talk about the conversion from the reactor. So we'll have to take care of all these three things when we are going to calculate the conversion from the reactor. So my dear student, we can write, if this is the reactor over here, if this is the reactor, if reactant is going to enter and it is coming, so here first factor you'll have to consider RTD, second factor you'll have to consider the types of mixing, and the third factor that you need to take care here, and that is equals to kinetics. All these things, three things becomes very important when we calculate the conversion from the reactor. So now just try to understand there are different models has been derived. I already have told you the modeling parameter becomes very important when we talk about the conversion. So there are number of modeling parameters that we'll have to study how we calculate the conversion. So first modeling parameter is my dear student, that is the zero parameter model. Zero parameter model. So in zero parameter model, it is divided into two subgroups. First subgroup is complete segregation model. Complete segregation model, and which is our objective of this session. We have to study the complete segregation model. And second is my dear son, maximum mixedness model. Maximum mixedness model. Okay, so these two subgroups is very important, but the objective of this session is to study about the segregation model and complete segregation model. But I am letting you some brief idea about the modeling parameter. So second parameter is my dear student one parameter model. Okay, second one is one parameter model, and again it is also divided into two subgroup. And the first subgroup is tank in series model. Tank in series model, and second is axial dispersion model, which we study in the will study in the subsequent classes. Axial dispersion model. So there are four models that we will have to study, and after that we'll get to know how the reactant fluid or reaction mixture is behaving inside the reactor, and how the conversion will depends upon the the surrounding fluid element, and different parameters like types of mixing, residence time, distribution, and the modeling parameters. So this is very important now. Now next thing here, one thing becomes very important, my dear student, here is the types of mixing that I have already told you, types of mixing. So there are two types of mixing. First we can see that is macro mixing, and another one is micro mixing. Okay, one is macro mixing and another is micro mixing. These two mixing plays a very important role whenever we talk about the conversion of non-ideal reactors. So when we talk about mitigation macro mixing, in macro mixing what happens, it produces a distribution of residence time without specifying how the molecules of different age group encounters with one another inside the reactor. Here here it will tell, I mean, whenever fluid element is coming, and actually if there is a reaction that is taking place inside the reactor is a liquid phase reaction. So macro mixing will demonstrate about how the fluid elements also interacting with the the neighboring fluid. Okay, but when we talk about the micro mixing, here it describes how the molecules of different age group encounters with one another inside the reactor. It will tell you the encountering fuels with one another. Okay, how the molecules encounters with one another inside the reactor. Now, so when we talk about macro mixing, it will define RTD. Macro mixing, it will define RTD. Okay, So whenever we only need the conversion from RTD data, I mean whenever there is flexibility that we will get the conversion from only RTD, then macro mixing will becomes very suitable over there. But so there are two extent of macro mixing also, because macro mixing is very important, that defines the RTD. So there are another two extent of the macro mixing. So first extent of the macro mixing that you can understand, my dear friends. So all molecules of same group, what happens over inside the reactor will remain together. Okay, just like plug flow behavior, all the molecules of same age group will remain together inside the reactor as they move from the reactor and are not mixed with each other age group. Okay, so molecules in this called as the complete segregated. In this case is complete segregation model. So let's try to understand how these molecules behaves like. So when we talk about, just like understand, this is a PFR. So here reactant fluid will be entering and here it is going. Okay, so I am just denoting it with the different colors, then you will understand. So these molecules here, okay, these molecules here of different age group. Okay, again I'm talking about here, again there are some coupling of molecules over here and it is having of different age group. Again there are molecules over here having different age group, and again there are number of molecules also there having different age group. Okay, so hope you are getting the thing why I am letting you to understand. Here having molecules have different age group is T1, here it is T2, here it is T3, and here it is T4. So what about complete segregation says? Complete segregation means molecules of time T1 group, age group, will remain together and will move forward inside the reactor at the same time. Okay, and molecules with the age group 2 will remain together and will move forward inside the reactor at the time 2. Just like there are a train, there is a train, and having number of compartments are there inside the train, and all the compartments are not connected. Okay, so first compartment is completely segregated, second compartment is completely segregated, third compartment is completely segregated. Okay, so the person staying in the first compartment is will be called as the complete segregated model. Why? Because molecules of that age group will coming together from the train whenever the train gets stopped. So this is the thing that you can understand, connect from there. So this is you can visualize the complete segregation model from there. So mixing, here you can say what happens over here. So whenever train is moving, every people is isolated in their compartment, but they are not going to mix. But whenever the train will stop on the platform, what will happen? Every people will be coming out their compartment to outside and will get mixed. So what happens at the latest position, the mixing will be there. So you can say that in the complete segregation model, mixing at the latest point. Are you getting? Mixing at the latest point. It's very important that you should visualize the thing, how complete segregation model works. So I have let you understand with the help of the example of the train and compartment. So hope you understand the concept of how the complete segregation model works. So this is the objective of our this session, how we can calculate the conversion by complete segregation model. Now when this happens, in this case what you can visualize in this model, it is assumed that the group of molecules having same residence time act as an ideal batch reactor. Okay, so just like try to understand, if we talk about the molecules of T1 residence time, I mean T1 age group, and molecules of T2 age group, molecules of T3 age group, and molecules of T4 age group, so they will remain completely segregated. They are not going to interact with the molecules of T2 age group or T3 age group or T4 age group. So in this condition, what we can assume, the molecules of T1 age group will work as a batch reactor. Are you getting? Here, if we can say, here molecules of T1 age group is staying, like here molecules of T2 age group is staying, because they are completely isolated, they are totally segregated. Here molecules of T3 age group is staying, and here, my dear friend, molecules of T4 age group is staying. Are you getting? So in this condition, they will be working as a batch reactor, isolated batch reactor. Are you getting? So Now, to find out the conversion in the exit stream, we must, calculate the average conversion. Why? Because here there will be some conversion, here there will be some conversion. So here there will be some conversion, and here there will be some conversion. Why? Because they are totally isolated, okay, segregated. So you have to do the average, no? Because this is the property of mathematics. When you do something, for different age group, so you'll have to calculate the average, and after that calculation of the average, that will be the final the calculation of that objectives. Okay, so here also, here you will be getting some x1 conversion, here you will be getting some x2, here you will be getting x3, and here you will be getting x4. So when we talk about this total segregated model, okay, because all these things are happening inside a reactor, and there are different conversions. So the overall conversion here, x overall, will have to convert, that is equals to x1 plus x2 plus x3 plus my dear student x4, and divided by 4. Are you getting? So this is the conversion that you can get from the segregation model, and this is the overall conversion, and which will be the average of all of the x1, x2, x3, and x4. Okay, up to this I think everything is clear how we are demonstrating the thing. Okay, now when we talk about segregation model, because here I have discussed these things on the basis of mathematics, but what actually we will do according to the perspective of the chemical reaction engineering. So here you can understand the thing, that is the average conversion. So if you have a residence time data, if you have RTD plot, it's very important. If you have RTD plot like this, if it is T and if it is ET, okay, and yeah, so sorry for my handwriting, it's not good, but I'm trying my best to let you understand the thing very easily. So yeah, so at dt time, it is always defined as the exit of the reactors. Okay, so first try to understand et, it is always defined at exit of the reactor. Of the reactor, first thing. Second thing is that already I have told you, in this model what will happen, the mixing will take place at the latest position, so that will be at the exit also itself. Okay, so can we calculate mean residence time, mean conversion, that is dx bar, that is mean conversion of the reacting fluid element spent time inside the reaction. Here if it is T, and here I am assuming dt inside the reactor between time T and T plus dt. Here I am assuming dt, so here it will be T plus dt. Are you getting? This will be d plus dt and it will be T. Are you getting? So you will have to understand this thing. So you can write directly dx bar, that is equals to my dear xt, because x conversion is a function of time, and you have mean residence time distribution plot xt dt. Are you getting? Or you can directly write here dx bar upon dt, that is equals to my dear student xt, and here it will be et. Okay, that you should know this thing, dx bar by dt. This is called as the complete segregation model. This is called as the mathematical derivation of complete. Now, when we talk about conversion, so integrate these things. Dx bar, that is equals to xt and et dt. Okay, dx bar is equals to xt dt, and it is mean conversion. Okay, so next thing, if we talk about my dear friend, first order reaction. I'm letting you to understand with the help of one example, and after that we'll let you know in the next lecture. If A to B, here rate kinetics is K and N is equals to 1. Okay. So can I write my resistance XA for first order reaction, that is 1 minus e to the power minus of KT. So can I write X bar, that is equals to, here it is XT and ET dt. Here it will be xty. It is function of time. So can I write my resistance x bar, that is equals to, here just write 1 minus e to the power minus kt, and here it will be et dt. So mean residence time distribution plot will be given, and I will let you know in the next exam, next lecture, with the help of one example. After that, you will get to know, and it will be 0 to t. Okay, so you'll have to integrate the thing, and according to that you'll have to understand the concept accordingly. Okay, so here it is first order reaction, conversion is for first order reaction, and mean residence time plot will be given according to that, and after that you'll calculate the conversion from the segregation model. Okay, so it's as simple as that. Once you do the example, it will be very easy for you to understand the thing. So in the next lecture I will let you know these things with the help of one example, and after that it will be very easy how we can calculate numerically. Hope theoretically I have completed the thing, and if you are facing any doubt, you just go through the video, and after watching the video, you will definitely get to understand the thing. Okay, thank you and all the best.